Okay, welcome to everybody. Let's start. So, the first speaker is Daniel Baumann from Amsterdam. And the talk is, the title is Inflationary Correlators from the Boundary.
Okay. Yeah, thanks everybody for coming early in the morning. Thanks to the organizers for putting together this wonderful conference and for inviting me to speak here. So I'd like to talk today about a new approach to computing and understanding inflationary correlation functions. And so I think this is important because in practical terms, everything we can ever learn about inflation will come from observing correlation functions. So they are fundamental observable, and so it's useful to try and understand these observables from as many different perspectives as possible, and I'm going to show you a new perspective today. So this is going to be work in progress together with Nima Akani Hamed at the IS, Hyun Lee, who's over there from Harvard, and Guillermo Pimentel, who's a postdoc with me in Amsterdam. But I should also mention that there's a large body of work by other people, many of them here, especially starting with papers by Xingang Chen and Professor Yi Wang, who's going to be speaking after me. And there's going to be two complementary talks by Yi Wang and Hyun Lee. So we try to kind of coordinate our talks a little bit so that there's not too much overlap. But I'm going to be starting off, and so I'm going to give you kind of the broad picture and kind of our new approach to the problem. So the outline is the following. I want to start with some motivation. Then I'm going to describe to you the method, and I'm going to show you a snapshot of results that we've obtained. We're currently writing a very long and technical paper. So I'm going to try and sketch out what the basic idea is, but some of the technical details will be, first of all, described by Hayden in the parallel session, or you should ask me about afterwards. But I'm trying to give you the basic idea right now. And I'm going to give some summary and outlook if I have time left. All right, so let me start with some motivation. So I think in the last 5 years or so, there has been a lot of activity trying to make precise an analogy between ordinary collisions in particle colliders and the measurement of higher order correlation functions in cosmology. And the goal today is going to be to make that correspondence between ordinary collider physics and cosmological collider physics as precise as possible. Okay? And so, in fact, I would claim that we have now, with this work we have achieved, in fact, to make this kind of correspondence really, bring it to its logical conclusion. And so that's what I want to show you today. So I want to show you an analytic understanding of cosmological correlators that parallels the way we think about, scattering amplitudes in flat space. So to explain to you what I mean by this, let me just remind you very briefly how we think about scattering amplitudes in ordinary quantum field theory. So at low energies, we can think of amplitudes, of course, as an effective field theory expansion. And so, for example, we can write this as a Taylor expansion in the Mandelstam variables S and T. So the lowest order contributions will come from some contact interactions, like 5⁴ interaction here. And then higher order Mandelstam contributions will just be higher derivative contact interactions. But at low energy interactions just look like pure contact interactions and can be described by an analytic function in the four momenta. And the cross section will also be a function of the Mandelstam variable. It will have some kind of shape like this. But if you go to higher energies, of course, this EFT expansion is expected to break down if it's truly an effective field theory. And in particular, it will break down at the threshold of new particles that are being created. So we can have resonances when the center of mass energy of our collision hits the resonance mass of a new particle. But the structure so it then becomes non-analytic. We can have poles. But the structure of the amplitude at that point is also very much fixed by thinking about the type of singularities that we can have. We can only have simple poles if the theory is local. And then the residues of these poles are fixed by unitarity or constrained by unitarity and kinematics to take very simple forms often. So for spin S exchange, for example, we have some coupling constant squared and then a dependence on the angle of the scattering, and that dependence is given by a Legendre polynomial of order the spin of the exchange particle. And I should highlight that this doesn't, although I was writing a Feynman diagram here, this kind of argument doesn't require any Feynman diagrams. It's purely thinking about symmetries and singularities that allows us to write down a structure like this. Okay. So of course, in the history of particle physics, trying to identify these resonances has been very important. And so this is just a classic plot of some of this. And so the question we'd like to ask today is, what's the analogous story in cosmology? What's the correspondent EFT expansion? What's the analogous features in cosmological correlators that correspond to resonances and so on? Okay. So as I said, in cosmology, actually, we don't measure scattering amplitudes. We measure correlators. The first snapshot we have of these correlators are, of course, the fluctuations in the cosmic microwave background. So we have found them to be correlated in non-trivial ways. These correlations, in fact, can be traced back to the origin of the hot Big Bang and can then be described simply in terms of a single scalar fluctuation, the curvature perturbation zeta. And we can reduce these temperature correlations into curvature correlations in zeta. And in particular, we have a theory, in fact, that gives us a nice way of generating curvature perturbations out of fluctuations in the vacuum. So that's what inflation, or the quasi-de Sitter phase, is doing for us. So vacuum fluctuations during inflation, of course, get stretched and produce two-point correlations in curvature perturbations. They also produce tensor fluctuations, and this is something, of course, we're looking for. So arguably, we have this nice mechanism of producing both scalar and tensor two-point correlations. However, these two-point correlations of scalars and tensors are slightly boring, one should say. One could say, not should. One could say, because they're almost completely fixed by symmetries. Yeah? So scale invariance completely fixes. If it was truly scale invariant, the Sitter expansion, you would just fix these two-point correlations up to an amplitude. So we now, okay, of course, we know that scale invariance is slightly broken, so we have a second parameter. There's an amplitude and a tilt to the spectrum. But nevertheless, there's very little dynamical information about inflation encoded, except for the tilt. There's very little dynamical information encoded in these two-point correlations. So that's why I'd like to study higher point correlations that do encode, much more momentum dependence and encode new information about the dynamical features and the particle content during inflation. So just like for scattering amplitudes, you can have contact interactions and exchange interactions. And so we'd like to understand today what these contact and exchange diagrams look like. And in fact, we would like to do this as analytically as possible. So what's the analytic structure of these correlation functions, both for contact and exchange interactions? And at a practical level, the reason also we're excited about this is that inflation happens at a very high scale, maybe as high as 10 to the 14 GeV. And so in principle, understanding these type of correlations would help us to identify features of particles with masses up to 10 to the 14 GeV. Okay? And so of course, this is a collider energy that we can only dream of on Earth. So we'd like to exploit the fact that nature might have given us this extremely powerful collider with center of mass energies up to those extremely high scales. All right, so let me sketch a little bit how we'd like to do this. So as I said, this is work in progress that we're hoping to finish anytime soon, meaning this year. So the basic idea is we want to study slow roll inflation, ordinary slow roll inflation, with a very weak coupling to massive fields. And what I mean by weak coupling is that there's some coupling interaction strength between the inflaton field and extra massive fields that lies somewhere in this range. So between the scale phi dot, the time evolution scale of inflation, and the Planck scale. If there's a cross-coupling between the fields that's mediated by a scale like this, then that would be described by what I'm going to be saying next. Okay? It's also possible that there are interactions that are stronger than that, and maybe Wang will talk a little bit about that regime, where the signal is boosted. Okay? But I want to be on safe grounds for the time being and study something that's just a weak perturbation to the inflationary dynamics. What this buys me, in fact, is that the correlation functions that we will find will be determined, to a large degree by symmetries. In fact, to a large degree by the approximate conformal symmetry at the boundary of the inflationary de Sitter spacetime. And so the basic idea is going to be to describe these correlation functions purely from the point of view of the boundary of the end final surface of inflation. And so that's why we call this approach time without time, because time will actually never make an explicit appearance in this approach, but it will somehow emerge from the momentum structure of these correlators on the final surface. So we will see how this arises. So symmetry will play an important role, but singularities will also play an important role. So symmetries alone will not fix these correlators by themselves, but when we think carefully about the type of singularities that are allowed, then the combination of symmetries and singularities will fix these correlators to a large degree, just like it happens in ordinary flat-space scattering amplitudes. So we will have to remove some unphysical singularities and correctly normalize physical singularities, and that will be very constraining. Okay, so let me give you, because this will be kind of technical, let me give you a quick roadmap. So what we will study as the main object in this talk is a very simple object. It's just a 4-point function. So 4 inflaton fields, or massive scalars. At the moment, it doesn't even have to be inflaton. With an exchange particle of mass m and spin 0, so an extra scalar. So rather remarkably, this object in inflation is not known analytically. It's kind of the simplest exchange diagram tree level that you can have, but we don't have an explicit analytic answer for this object. And so I'm going to show you an answer for this object based on the symmetry approach. And actually, this object is less special than you might think, because we also were able to identify ladder operators that allow us to take the answer that we get for scalar exchange and promote it to higher spin exchange. Any spin can be generated by just acting with a simple operator on this fundamental object, tree-level scalar exchange, to generate tree-level exchange of any massive particle with any type of spin. Moreover, we don't have to just focus on 4-point functions. If we take one of the legs of this 4-point function and evaluate it on the background, or take its momentum to 0, we get a 3-point function, and so we get standard inflationary 3-point correlators. So for example, if you take this internal field to have 0 mass and spin 0, so make it a graviton, you actually are able to reproduce Maldaceno's standard answer for the inflationary 3-point in a kind of a quick way. And you classify all kinds of new type of interactions as well. Okay, so let me say a little bit. I have to define a little bit of notation for this object. So we're studying a 4-point correlation function of scalars with momenta k1 to k4. By homogeneity and isotropy, this has the following structure, that there's a momentum conserving delta function, of course. So these momenta have to form a closed quadrilateral, 4 points closing, okay? And then the remaining function is a function of 6 momenta, and I can choose these momenta to be the 4 different sides of the quadrilateral, and then 2 sums. So for example, this diagonal, which I called S, in analogy to the Mandelstam S variable, and there's another one T, which is to say the analogous to the Mandelstam T variable, but now 3-dimensional. So this is a function of 6 scalar variables. It's useful to actually define dimensionless variables, so take the ratio of the sum of 2 of the momenta and this diagonal momentum S, this exchange momentum S. So this will give me 2 variables called U and V. And in fact, conformal symmetry will reduce the number of independent variables in this function here from 6 to 2. And these 2 variables, U and V, are going to be the variables that we will always be using to describe the momentum dependence of the fundamental object. Okay? So in the end of the day, we will arrive at functions of 2 variables, U and V, which are these 2-dimensional less momentum ratios, one describing the sum of these 2 lengths, and the other one describing the sum of these 2 lengths. Okay? It's also useful to factor out the scaling dimension, the mass dimension of this function f, and so we can define new functions f hat that are dimensionless. Okay. Okay, so that then automatically satisfies scaling symmetry. We have 3 more symmetries when we have a conformally invariant background, and so these three additional symmetries, in fact, can be summarized after some work into a single equation acting on this dimensionless function f hat. A single differential equation as a function of this u variable and this v variable, where this is just a differential operator that takes this form here. Okay. So this is so once I'm satisfying this partial differential equation, I will satisfy all the symmetries on the boundary of the space-time, and I can. The goal will be just to classify solutions to this equation eventually. So what does this equation describe? So this equation will determine the momentum dependence of the 4-point function on the final surface. And so, for example, evolving in the variable u will describe what happens when I take this quadrilateral and I'm stretching the two sides of the quadrilateral, here holding the other two sides fixed. That's what the evolution in u will do for us. And similarly, evolving in v will keeping these blue sides fixed and stretching the red sides of this quadrilateral. Okay? So in some sense, these momentum operators, differential operators as a function of momentum, they are encoding what happens in the bulk of the space-time as an evolution in time. Okay? So the time dependence of the evolution during inflation will be encoded in momentum dependence through this differential equation. So you're trading time dependence in the bulk for momentum dependence on the boundary determined by this differential equation. Okay? So in the rest of the talk, in fact, I will, conceptually I want to do something very simple. I just want to classify solutions to this equation, and that will allow me to classify all 3 and 4 point functions with this weakly broken conformal symmetry. So the simplest solutions to this equation, in fact, correspond to contact interactions. So 4 point contact interactions like this. You could check easily from the previous slide that this simple function here satisfies the constraint equation. And then you can generate an infinite tower of higher order interactions corresponding to higher derivative contact interactions by acting with this u operator n times, or an arbitrary number of times. It creates an infinite tower of higher derivative interactions in the bulk and contact interactions on the boundary. These contact interactions, if you look at them, actually, they're classified kind of by the order of the singularity in u plus v. And this u plus v, in fact, describes the u plus v going to 0 limit, describes actually when the sum of the energies of the external states goes to 0. So that's a special limit that you can't take physically, but you can analytically continue to that limit. And it turns out that the contact interactions are classified by the order of the pole in the sum of the energies going to 0. So this is sum of the energies. So this would be 1 over k total, or 1 over the sum of the energies. And this would be 1 over the sum of the energies to the power n. Okay? So as you go into higher contact interactions, you get higher poles. Okay, the next thing we want to describe is tree exchange. And so in the case of tree exchange, we can actually reduce this partial differential equation to 2 ordinary differential equations like this, where we now have split things into an evolution in u and an evolution in v. And it's symmetric in the evolution in u and v because of exchange symmetry of the scalar particles on the external states, with an integration separation constant that's just the mass of the exchange particle, and a source term that's simply given by the contact interaction that I showed you previously. Because if you look at these equations, take the mass to infinity, I should be reducing to a contact interaction. Then take an exchange particle and make it infinitely heavy, it reduces to a contact. So in this differential equation, you see if you take the mass of the exchange particle to be infinitely heavy, this 4 point function reduces to contact. Okay? And this is very much the same as if I take a scattering amplitude and I multiply it by an inverse propagator, I'm left with an analytic function that's just an expansion into contact interaction. So the content of this kind of equation is the analog of that in scattering amplitudes. But now, given that we have classified all possible contact interactions that respect our symmetries, we can now try to solve this equation under this classification and classify all possible exchange interactions that we can have. So formally, if you just look at this equation, you could try and solve it by just inverting this differential operator. So you can then write a formal solution to this equation, which is just an infinite series of this differential operator delta u acting n times on the source. Okay? So just like you can expand out the propagator to an infinite series in Mandelstam variables. This will give me an expansion in powers of h over m squared. So, and at all orders, this will be an analytic function. Okay? And in flat space scattering amplitudes, this expansion, in fact, would be exact, at low energies. So that's just the analog of the EFT expansion that we have in flat space for this correlation function. However, in the case of cosmology or inflation, we know physically that we should be missing an effect, because the space-time is rapidly expanding, there should also be the possibility that we're spontaneously creating these particles out of the vacuum, and then they decay into 2 inflaton particles on both sides and produce this exchange interaction just spontaneously by particle production. And we expect this to be an exponentially suppressed effect, e to the minus m over h. So rather than this being a power law suppression h over m squared, there should also be an effect like this. And our equation actually knows about this. So what we have been missing so far when we were just writing this is homogeneous solutions to the equation. We could add any type of homogeneous solutions, and those homogeneous solutions, in fact, will be creating effects of that order, these particle production effects in the expanding space-time. However, at this level, actually, there's a large degree of freedom of adding homogeneous solutions. So we have to find a way of actually identifying the unique homogeneous solution that's allowed. And so the way we do that is, as I alluded to earlier, is by thinking about the allowed singularities of the problem. So for example, if I add a generic homogeneous solution to the problem, I would generate a logarithmic singularity like this one. In our old variables, that would correspond to a singularity that lives somewhere on the diagonal. So if I just take two of the sides and I'm collapsing them onto the diagonal, and then there's a whole line worth of singular behavior of this function. And that's something that should be absent in the standard vacuum. So one of my collaborators likes to call this a garbage singularity, so you can guess who. So we would like not to have this singularity if we're starting from the standard Wunsch-Davis vacuum. Excited state would have this type of singularity, but the standard Wunsch-Davis vacuum does not. So we're going to add homogeneous solutions in exactly such a way that we're not creating this type of singular behavior. There's actually a second singularity that is physical in the unphysical reason, and we keep that one and normalize it to have unit amplitude. And those two constraints by themselves fix the two independent homogeneous solutions that we could have, and completely fix the solution uniquely. Okay. So this is what the solution looks like, taking a limit of small u. So in the limit of small u, the solution has two pieces. One of the pieces is the EFT expansion that I showed you earlier, but now written as a Taylor expansion in the ratio of the momenta that I introduced. This is purely analytic. And then there's a second oscillating piece, depending on the log of the ratio of these two momenta, that in the limit of large masses, in fact, has an amplitude that scales as e to the minus m over h. And so that's characteristically, this is non-analytic. It's not an EFT expansion, but it's an extra effect that I get due to the expansion of the space-time. So this corresponds to the particle production in that space-time. So just by solving this differential equation that dictates the symmetry structure on the final boundary, we find both of these solutions. We find a low-energy EFT expansion piece, and we find spontaneous particle production simply as a solution to this equation. So this is a slightly simplified limit so that I can show you. In general, this equation looks the same. This expansion is a little bit more complicated. This solution looks a little bit more complicated. It's written in terms of hypergeometric functions. But morally, it looks something like this. Okay, so there's a number of nice things you can do, and I don't have time to describe all of them. Once you're handed an analytic answer, or an answer like this to these correlation functions. So for example, what you can do is you can analytically continue the solution to the complex plane. So the complex plane in U in this case. And so it turns out in the complex plane, this function looks something like this. Okay? Well, not something like this, it looks like this. And so it has a branch cut on the negative real axis between -1 and 0 in this dimensionless variable. And more remarkably, actually, if you look at what's the amount of discontinuity, the jump, as you're crossing this branch cut. So if you calculate something like this, take the discontinuity of the function, actually first derivative of the function, evaluate it at this particular point, which again is the point where the sum of the energies goes to 0. What you find is actually that you reproduce exactly the flat space amplitude. So in some sense, the flat space scattering amplitude is encoded in the analytic structure of the cosmological correlator. Okay? So there's somehow a rather deep relation between curved space particle production, which is given by this piece here, and flat space scattering, which is given by the scattering amplitude. So the first time I saw this is like magic. Okay? So I'm happy to talk about this endlessly, but so you should come to me afterwards if you want to hear more about this. Okay, but let me come back to the structure of the solution. This was a little bit of a digression. So remember we had two pieces. We had an EFT piece and we had a particle production piece. There's a special limit you can take, which is famous for, I'm sure, all of you, which is if I take the 4-point function and I'm collapsing the diagonal momentum, or I take the 3-point function and collapse one of the side lengths. Yeah? So either the collapse limit of the 4-point function or the squeeze limit of the 3-point function. In that case, we know that the EFT expansion actually vanishes. This is the limit u going to 0 of the 4-point function. So we had this power law in u, this will vanish. And then we're left with this purely non-analytic oscillating piece. And so you will see oscillations that are with a frequency that's determined by the mass of the particle. Okay? And so that's precisely the analog of a resonance in collider physics. Okay? If we look at what if we also ask when we approach this squeeze limit, we can approach the squeeze limit in different angles. And so there's an angular dependence in this squeeze limit. And you can show that that angular dependence is precisely given again by a Legendre polynomial of order the spin of the particle. So in this particular limit, it's the imprint of this massive particle with possibly spin is very distinctive. It has oscillations with a frequency given by the mass of the particle, and it has an angular dependence given by the spin of the particle. Okay? And that's also the same we expect to see in collider physics, where the final state has an angular dependence that's given by the Legendre polynomial of order the spin of the particle. Okay? The reason this arises is really very much analogous to the reason it arises in flat space scattering. It's just kinematics of the polarization structure of the internal state. Okay, so I think what we have achieved with this new work is that we have kind of completed the program of the cosmological collider by connecting, the equilateral momentum EFT contribution with this particle production piece in a single kind of unified description. Just like in scattering amplitudes, you have a low energy EFT expansion and a resonance, and we learn a lot by studying kind of the shape of the resonance and how we approach that resonance from the EFT regime. And so we hope to learn equally large amounts of information by being able to study the full shape of these 4-point and 3-point correlations at all momenta. And so we now actually have kind of these functions available at all momenta, and they're able to approach this kind of oscillating regime from the top. Okay, can anybody tell how much time do I have left? 2 minutes, okay. So I'm almost done. So just to summarize, what we have done is we have derived the most general 3- and 4-point functions arising from massive particle exchange and inflation in this regime of weakly broken conformal symmetry. I showed you the explicit result for the exchange of a massive scalar, but using ladder operators, actually this can be related. That fundamental object that I showed you actually transforms into an object that includes all spins of particle. I showed you a 4-point function, but this is also very simply related to a 3-point function by a simple transformation. So it's kind of nice that this one simple object, a scalar exchange between 4 inflaton particles, is related by simple transformations to spinning particle exchange between 4 inflaton particles and a 3-point inflaton interaction. And so you can then check various things. You can reproduce a lot of classic results in the literature. You can produce Maldaceno's, if you take this to be a graviton, you produce Maldaceno's famous 3-point correlation. If you take the simplest contact 4-point and evaluate one leg on the background, you reproduce Criminelli's partial phi to the 4th 3-point interaction. So things like that you can just check very quickly. And you get a classification of an infinite class of new things, okay, with these properties. Okay, I should admit, at the very end here, and then I think Yi and Hayden are going to say more about this, that the signals I described in this talk will be very hard to observe, okay, realistically, especially in this regime where I was enforcing that the conformal symmetry of the inflationary backbone was not strongly broken by the interactions between the massive field and the inflaton. Because what that means, if I think about non-Gaussianity on this kind of scale, so I'm introducing FNL in a slightly different way, where FNL order 1 corresponds to the completely non-perturbative regime, where second order corrections are big, too big to be treated perturbatively. and purely gravitational interactions would generate the ordinary single field slow roll at a 10 to the minus 7 level. Okay, on that type of scale, we would have to be living in the regime between the 10 to the minus 7 and 10 to the minus 5. Okay, at the lowest two orders of magnitude before you hit the the standard inflationary non-Gaussianity. So it will be hard to see unless you have some way of boosting and getting into this regime here, which is not so hard to do, but then the symmetry-based approach becomes less powerful. Hard to see, but nevertheless, if you could see something like this, extra massive particles with possibly spin, in my mind, this would be the most direct probe we could possibly have about the ultraviolet completion of inflation. We think, if you complete, single field slow roll, it has to have some extra new states, and it would be nice to see remnants of these extra degrees of freedom, so that we have some positive detection of something rather than an argument for the absence of something that isn't there. So maybe I stop here.
Thank you, Daniel. Very inspiring talk. Any questions?
I have a question about the particle production part.
Sure.
You showed that in the large mass limit it suppresses like e to minus m over h, but I'm just wondering it's more like e to minus m over Hawking temperature. So is it a precise expression or just an order of magnitude argument?
I dropped a pi. Usually it's e to the minus pi h over m, but I didn't want to blur your eyes with a pi. But it is precisely the Hawking temperature, and you get a pi from that. So it's e to the minus pi h over m. I absorbed the pi into m.
Another question? Yes, please.
So you are saying you are studying the energy scale higher than phi dot. So I expect if you have lower than phi dot, the Feynman diagrams are still perturbative. So I don't know what goes wrong.
No, I think what goes wrong is just that you break conformal symmetry kind of in a stronger. Nothing goes wrong. It's just we went to a lamppost where we have this weakly broken conformal symmetry. So they had this simple differential equation that constrained the full answer, and we can classify everything as very nice, I think. If you go outside of that regime and you couple the fields more strongly, these equations don't fix the structure. There's nothing wrong. I mean, we had a previous paper where you can still then just write down a Lagrangian, compute, just integral in calculation way this 4 point. But these, but the nice thing here is you don't need a Lagrangian. It's just purely symmetry based, and it gives you analytic answers. So you can do kind of fancy things about studying things in a complex plane and asking about how things are related in a complex plane. That's not something you can do if you write down a Lagrangian and just integrate over time.
Any questions?
So I think you showed some feature on the particle production on the correlation function. But
yes.
If you find many degrees of freedom, can you identify some simplistic feature? Because the signal may be much more complicated if you have many signals.
It's a question whether, it would be interesting to see if you can, so if you have not just one particle but several particles, then the most naive guess would be there's just a simple superposition of these many particles. And then, well, you would see the lightest guys because these get exponentially suppressed as they're more heavy. So there's actually not that much room for seeing a large spectrum of particle. You would see the light. If you have a large spectrum, that would be nice because actually you have a larger chance of seeing something that's close by, near the Hubble scale. So that's a possibility. So the more complicated story would be if these extra particles are interacting amongst themselves, and then you would have to again take that into account. But that's a technical complication, not really conceptual, I think.
Okay, thank you.
It's a related question, I guess. What exactly would you see? What is the observational signature in your window of opportunity?
Oh, okay. So it's something like this. This is precise. So what I'm showing here schematically is kind of, here I'm showing a 4-point function, but for a 3-point function it would look the same. I'm showing the 4-point function or 3-point function as a function of the ratio of momenta. So imagine I'm taking the squeezed limit. What's shown on the x-axis here is kind of the ratio of the long momentum, low momentum, to one of the other sides, and I'm scanning that momentum. So as I'm squeezing the triangle more and more, I'm going along this axis towards the left. So at first see some characteristic shape corresponding to the EFT part, the regime where I can think of this as being integrated out massive particles. And then would start oscillating with a frequency of order the mass of the particle. So what you would literally see is this. You'd like to hope to see this shape. Yeah? And then there's a second dimension. I took a slice. These are two variables. I would see there's a second dimension where the shape looks the same but slightly shifted because the second variable also evolves. But what's nice is we have the full function in 2 dimensions for all values of these things, no limits taken. And so in principle, you could try and fit your data over all momenta, from small triangles to squeezed triangles.
Very good. So let's thank Daniel again. Okay, so can you speak that is a U1 and is a follow-up, is inflation as a particle collider?
All right, thanks a lot for the invitation. And today, I'm going to continue to talk about the cosmological collider physics. And I first will start from a recap of the cosmological collider physics, but from the bulk point of view instead of a boundary. And then I will tell you what we can do with the cosmological collider. What kind of physics can we study? So first, let us start from very general features of high energy physics. That if we see the new physics in terms of the energy scales, you are observing that statistically, the new physics appears as logarithm in energy scales. But if we are building colliders to detect this kind of new physics, we are kind of the cost of the collider is energy to some power. For sure, it is still important as ever, to push the energy frontier to build the colliders. But on the other hand, it's also interesting to think about complementary ways to study the high energy physics, that if the nature already have built some collider for us, and all the things that we have to do is to build detectors to find out the data and do the data analysis. So we need to search for the high energy events in nature, and they are hiding in extreme conditions, for example, the black holes, and recently there are stories about black holes and actual high energy cosmic rays. And today I will focus on the other extreme condition, which is the early universe. The early universe, so for inflation, the energy scale of inflation can be as high as up to 10 to the 13 or 14 GeV. So it's an interesting question to think about if we can use inflation as a collider. So to talk about this question, we first need to think about what is a collider in some general sense. So what is a collider? A collider can be thought of as follows. So first of all, we need to have some very high energetic process happening, and there are some heavy particles produced by these colliders. And afterwards, so we know this very high energetic process is happening with a very low time scale, which corresponds to that it's very hard for the detector to respond directly for that signals. So we have to rely on some long-lived signals to carry over the outcome of these colliders to what we can access on the detectors. And for sure, for the man-made colliders, the high energy particles are created, for example, by the collision of the IHC, and the long-lived signals correspond to the leptons, photons, and jets, and the detectors are corresponding to Atlas and CMS, for example. Very interestingly, in our universe, we have very similar setup for a collider. Namely, the primordial universe, so the leading theory is inflation, and inflation says that there is indeed an energy scale where the particles are produced which is the Hubble scale during inflation, 10 to the 10 to, up to the 10 to the 13 GeV. And there is a effective way to understand how the particle produced, which is the so-called Gibbons-Hawking temperature, can be considered as that there is an effective temperature, so the particles are produced in this effectively thermal system, although it's pretty strongly gravitating, so it's not ordinary thermal system. So indeed, we have the particles produced, and now we are living in the late universe, so we cannot directly travel to the early universe to see the signals. So what can we do? What we can do is, fortunately, there are the conserved quantities, which are the curvature perturbation zeta, and also the primordial gravitational waves, gamma ij. And if we are fortunate, there may be some decoupled isocurvature fluctuations, which are highly constrained at the moment. So they are the conserved quantities that they live very long, and eventually they can be detected from the cosmological observations. For example, the cosmic microwave background, which is the major thing for the study of non-Gaussian now. And in the future, near future, there will be large-scale structure. Actually, the study is already going on, and there are 21 centimeters in a bit distant future. So indeed, our universe, in this sense, really looks like a collider. So we'd like to see what kind of physics can be studied on this collider. So what kind of physics can be studied? Before talking about the physics can be studied on a cosmological collider, we can recap what kind of physics can be studied on, in general, on a particle collider. So we can study the mass of the particle, we can study the spin of the particle. So the mass of the particle can be considered as a resonance, which is the emphasis also for Professor Baumann's talk, and you have heard the story how to calculate that from the boundary. And the resonance is considered to be the energy dependence for the correlation functions, and the spin can be considered as the angular dependence of the correlation functions. And there are some interactions which tells you what kind of precise model do you have for the collider physics. And for the cosmological collider, again, we have something very similar. And so there are, again, the mass and spin and interactions. So today, because of the time limit, I'm merely talking about the mass. But before talking about the mass, let me first have some very general discussion about we can classify the different kinds of signature into two classes. The one way, the one class is kind of the our traditional understanding of how we can extract data, the high energy physics data from cosmology. So traditionally, what we are doing is first we build inflation models from particle physics. And based on these inflation models, we are going to see what kind of cosmology do we predict. And then from the prediction of kind of cosmology, we are seeing, so what are the particle physics model and what kind of parameter do we have in this particle physics model. For sure, this is important, but there is one difficulty, that so far there are so many inflation models. I don't know if there are thousands of, but at least there are hundreds of inflation models. So it's really difficult from the limited data that we get in cosmology to pin down which exactly inflation model do we have, and then to study the particle physics within that model. So what we are recently trying to do is trying to decouple these two processes as much as possible, in the sense that, first of all, the one thing is trying to pin down the inflation model. But here, the other thing, the so-called cosmological collider physics, is trying to decouple that. We don't really care what kind of inflation model do we have. But as long as inflation can be considered as quantity zeta expansion, so the scale factor is almost exponential as a function of time, then we can model independently, study the particle production during inflation, and then study the mass and spin mass and spin information. Yeah, we are not really getting to interactions because interaction is highly model dependent. So this is the general idea. And here, let us see what is the resonance. Again, so Professor Baumann already talked about the resonance in the boundary point of view, and here I'm talking about the bark point of view, which is in terms of the computational precision is already a bit outdated because Daniel already gave the analytical result, but still I think it's still intuitive to see what's happening in the bark point of view. So when the fluctuations are generated during the inflationary expansion, so why there should be such a resonance? So how the resonance comes is because of the something similar to a thermal environment. So we have the thermal, almost the thermal production of the heavy particles. And once the heavy particle is produced, there are associated production of the curvature perturbation, which are light fields. So there is a preferred time moment for a given kind of heavy particle, and the preferred moment for this kind of particle is produced is that the associated curvature perturbation has the same physical wavelength compared to the wavelength of the massive particle. So this is the preferred time, and this is considered to be the resonance, because the massive field is oscillating according to the mass of the particle, if it is an underdamping oscillator, and the light field is oscillating according to the conformal time. So there is a time, which is the resonance time that the production has the largest rate. And afterwards, the universe expands. So the originally pretty short wavelength modes become long wavelength modes, including the massive field and also the massless field. But recall that the massive field, if it is non-relativistic, the intrinsic oscillation frequency is still determined by the mass of the field. So it is still the same frequency. So at the decay time of the massive field, there is another resonance happening, and it decays to the preferred wavelength for the decay product is the same physical wavelength as initially the physical wavelength of the production associated production for the curvature perturbation. So what you are getting is there are long wavelength fluctuations and there are short wavelength fluctuations. They are correlated by this production and decay of the massive field through this resonance. So this is the resonance. And the next question you are asking from here is, how do we make use of the resonance, or what kind of correlation do we have for this short wavelength and the long wavelength fluctuations? The kind of correlation we have is actually an interference effect, because between the production time and the decay time, the massive field propagates for some time, and from the elementary principle of quantum mechanics, the massive field changes by a phase, e to the I m, the time difference between the production and the decay. So once the massive field changes by a phase, this phase can be translated into the wave number at the production time and the decay time. The translation is because, so you have time here, and time is a logarithm of scale factor, and the scale factor at production and decay is characterized by the resonance. So you can insert the k into the logarithm of this equation, and you are getting the decay wave number over the production of wave number to some imaginary power. So this imaginary power is non-analytic. That means this kind of effect is intrinsically the particle production, some additional particles, which cannot be mimicked by a single field effective field theory. So this is considered to be the interference between the short wavelength and the long wavelength fluctuations. So this kind of effect is the so-called non-Gaussianity that we are expected to see. So for sure, so from the conceptual simplicity, I was showing you the 4-point correlation function, but in terms of the observation signal to noise, it's more important to observe the 3-point correlation functions, and the interference predict a special shape of non-Gaussianity. That as we are going to squeeze the limit of non-Gaussianity, that if we keep one of the k fixed and the other two k's are larger and larger, then we are getting this kind of oscillations. And here, so these different curves are for different values of the mass. So this is the kind of interference, or this is the signal that we are actually seeing, and that I think that also answers one of the questions of the previous talk. And So here, up to now, I'm trying to convince you that our universe indeed looks like a collider. And once it is a collider, the next question is, what kind of high-energy physics can we study on this cosmological collider? So what's happening on the Hubble scale? There are two classes of physics happening on the Hubble scale. The one class of physics is accidentally, they are near the Hubble scale. For example, if in the near future, we are going to see the primordial gravitational waves, that means inflation is really at a pretty high energy scale, for example, 10 to the 13 GeV, and that corresponds to that the grand unification and the neutrino seesaw may be just a few orders of magnitude higher. So up to some coupling constants, there may be massive states accidentally lying near the Hubble scale. So this is one possibility. And the other possibility, actually a more generic one, is that there are some other physics which originally they are living at very low energy scale, but they are uplifted to the high energy scale due to the environment of inflation, which is a time-dependent background. The best example of that is the particle physics standard model. For the standard model, we know the energy scale of the standard model is largely determined by the Higgs mass, which is 125 GeV, and inflation is most probably much higher energy scale than that. So naively, we would thought that the standard model fields can be considered as massless fields during inflation. But this is not the case, because during inflation, assuming the Higgs originally is pretty massless, then the Higgs field will get a non-trivial two-point correlation function, which is of order Hubble square. Then take a look at the self-interaction of the Higgs field, the lambda phi 4 interaction. If you take part of the interaction to be the classical background and the other part as quantum, then you are getting an effective mass, and the effective mass up to some coupling constants of Higgs is of order the Hubble parameter. So once you get the Higgs mass of all the Hubble parameter, everything else in the standard model are Hubble parameter times some coupling constants. And there is also another possibility that the Higgs field can non-minimal couple to the richest scalar by Higgs square R coupling, which satisfies all the symmetries of the standard model as well as the general relativity. And the richest scalar during inflation is of order Hubble scale. So again, you are getting some effective mass of the Higgs of all the Hubble parameters. So, and of course, this term cannot be measured on colliders, so we don't know the size of this term. So if we study the standard model in the cosmological collider, we had better to study, consider the Higgs mass as a free parameter and see how the other things scale according to the Higgs mass. And I'm not going into the details, but if the Higgs mass is large, if the Higgs is small mass, then the WZ gets larger mass. If the Higgs has higher mass, the WZ has smaller mass. This is because if the Higgs is light, the Higgs fluctuation can be very large, enhanced by the Efonian numbers. And once the Higgs fluctuation is large, the WZ gets the mass from the Higgs fluctuation, so they are large. And if the Higgs is heavy, the fluctuation is small, so the WZ are pretty light. So this is about the standard model. And there are other things that can be considered. For example, the supersymmetry breaking, which is considered by Baumann and Green and also other people, that we know that most likely supersymmetry cannot survive in de Sitter space. And the minimum breaking scale of supersymmetry is the Hubble scale. So originally, if you have some states whose mass is protected by supersymmetry, then after the breaking, their mass is naturally of the Hubble scale. So they also lies in the range of where the cosmological collider can study. So they are at the energy scale of the cosmological collider, what kind of particle physics can we study? And so far, we have been discussing something very parallel to our ground-based colliders. Simply, we have hopefully a higher energy scale. But now, let me talk about something which are pretty unique for the cosmological collider. For the man-made ground-based colliders, we know perfectly well how the colliders are built. So we don't have to study the outcome from the collider to study how the collider is built. But for the cosmological collider, it is different, that we don't know exactly what's the physics of the primordial universe. So by studying the cosmological collider, we also hope to recover what physics actually happened in the primordial universe, including the expansion history and also the test of quantum mechanics and the correction of the two-point function and consequently the NSR diagram. So here, let me focus on one thing, which is the expansion history. Even if you do not work on inflation primordial universe, you may know that last year there is a debate even in the context of popular science about if inflation is a nice theory or not. And the fundamental thing about the debate is there are some alternative theories of inflation. So for sure, inflation is the leading theory, and in my mind, the best theory explaining everything that we have observed so far. But it's actually a bit embarrassing that we are saying we are in a precision era of cosmology, that we measure our cosmological observations really well. But if we know our universe really well, how comes that we don't even know the primordial universe was expanding or contracting? So there seems to be a contradiction. And actually, indeed, we know some aspects of our primordial universe very well, but not all the aspects. The aspects we know our universe very well are the size of fluctuations as a function of scales. We measure them very precisely on the cosmic microwave background. And how to interpret that in terms of the primordial universe? In the primordial universe, the size of fluctuation as a function of scale. So the scale can be considered as the horizon crossing scale, which means the conformal time. So in the primordial universe, we understand pretty well that at a given conformal time, what is the generated density fluctuation? But there is a difficulty that by only knowing the conformal time, we are unable to construct the evolution history of the primordial universe, say the expansion history. So we really need the physical time. The problem can be very roughly considered as that, so if we have a movie, but now, by only knowing conformal time, it's like we know every frames, but they are stacked together that we don't know the physical order, the physical time of the movie. So as a result, we don't even know for very sure that our primordial universe is inflation or not, although inflation is highly preferred. And at this point, the massive fields come to help, because the massive fields has oscillations and the interference effect, as we were discussing. And the oscillation of the massive field is according to the physical mass of the field instead of conformal time. So as a result, the oscillation is a sine cosine function according to physical time instead of conformal time. So by seeing the oscillation according to scales, so recall that scales corresponds to conformal time and the oscillation corresponds to physical time. So and the scale corresponds to conformal time. So once we see the oscillation as a function of scales, actually we are seeing the correspondence between the conformal time and physical time. Differentiating this equation, we get the scale factor. So actually the cosmological collider physics, to see it in another way, is a direct probe of the expansion history of the primordial universe. And actually we can do more precisely that if we model the scale factor as time, physical time to some power. Here, P approaching infinity corresponds to inflation. And alternative to inflation, in general, corresponds to P is some number, order 1. So by measuring the correlation function very precisely, we can see that inflation is this kind of profile, and other alternative to inflation scenarios corresponds to different profiles. And they can be written in terms of the three-point correlation function that is a oscillation of the hierarchy of scales to the 1 over P power. So this 1 over P is almost the inverse function of the scale factor as a function of T. So we are really directly seeing the expansion history of the universe by measuring the three-point correlation function of the primordial universe in a very precise way. So far so good. But it's cheating if we don't come to the difficult part, which is observations. And for the observations, the most important question that you wonder is how large is non-Gaussianity, or how large is FNL? And the FNL, first of all, we don't know. So in the very, very, very best luck, they may already in, say, the Planck data, but people, if people use the correct templates, they are emerging. Yeah, but this is too good to be true. So the FNL for this model can be considered to be, there are three parts. The first part is some normalization factor, just the definition of FNL. There are some normalization factor, something 10 to the 4 or 10 to the 5. And then it is surprised by two parts. The one part is the coupling, and the other part is Boltzmann. The coupling part is corresponding to the, so in weakly coupled quantum field theory, once we have vortices, the vortex had better to be perturbative. And first of all, we don't know how strong is the coupling. We, in some sense, can get a lower bound of the coupling according to Cunningham and Madasina. So the worst case is if we trust that inflation is described by an effective field theory, the cutoff scale of the effective field theory is lower than Planck scale, and beyond the cutoff scale, some other generic terms can emerge. So if we trust this picture, then the lower bound of the coupling contribution of the FNL corresponds to, maybe I'm writing in a bit confusing way, corresponds to this normalization factor times coupling. The overall factor is of order epsilon, which is very small. So even for the distant future 21 centimeter experiments. So there are some hope that we probably could have larger couplings. For example, if we hope efficient reheating of the inflaton eventually to the standard model fields. So if the reheating is not gravitational reheating but stronger reheatings, there has to be some higher couplings. And also, so Baumann and collaborator discussed some naturally defined effective field theories with pretty high, but for sure not as high as Planck scale cutoff. And in this kind of theories, so the relatively larger signal of non-Gaussianity naturally emerge. So this is the coupling part. And there is also the Boltzmann part. The Boltzmann part, meaning that we are saying that the cosmological collider is sensitive to mass of order Hubble. And we can look at this relation into a little bit detail, that if the mass is smaller than 3/2 Hubble, then there is no Boltzmann factor. And actually, there exists a IR growth, means that the field is pretty light. So on super horizon scales, the field can still interact for a few epochs. So there is an IR growth factor. So this is the light mass case. And the large mass case, there will be a Boltzmann factor similar to what happens in the thermal physics. And this thermal factor is naturally this kind of foam. And as Yokoyama-san correctly says, there is a pi factor. And so this is the usual Boltzmann factor. And there are some hope that it may also be enhanced by, for example, the energy scale phi dot, for example, the temperature during inflation, if it is not minimal temperature in some very special models like warm inflation, and also can be enhanced by some potential energy of the interaction, namely the chemical potentials. So this is roughly how large is FNL. But the take-home message for FNL is actually we do not know how large is FNL for this kind of models, because the size of FNL is very model dependent. So we were talking about the model independent features, which is the shape of non-Gaussianity. But the size of non-Gaussianity in here is very model dependent. So it's pretty similar to primordial gravitational waves, that we know what we are going to see, which is a nearly scale invariant spectrum, but we do not know the value of the tensor to scalar ratio until we see it. And so this is the history of probing non-Gaussianities, and Professor Komatsu is the main force to push this forward. That from 2 decades ago up to now, so we are making great progress. And in the future, some of the experiments, for example, Sphere X, propose a 1 order of magnitude improvement for the precision of non-Gaussianity if they are founded. And in the very distant future, we have hope for a few other orders of magnitude if we can get rid of the difficulty from the experiments. So in terms of the collider terminology, the cosmological collider is something that we have very high energy scale, but very low luminosities. So we need to really build the detector very well to catch as much motes as possible in our universe to recover this kind of very low luminosity signal. And as a brief recap, so we have been talking about how our universe looks like a cosmological collider, and what is the physics of a cosmological collider, namely the resonance, and what can be studied, namely the standard model, supersymmetry, and some accidental physics like the gas and neutrinos. And actually, the cosmological collider is also considered to be a direct probe of the evolution history of our universe. That's it. Thank you.
Thank you, Yuan. Well, thanks for the questions. Let me start myself. I didn't get at the end the conclusion when you compared inflation with the ekpyrotic case. So at the end, you think it's a way, there is a complete way to make the difference between the two that we can be tested, that it can be checked experimentally? When you compare the ekpyrotic and inflation,
right.
You have this nice plots.
Right. Yeah. So here, first of all, we have computed the shape of non-Gaussianity in the ekpyrotic phase, which we are pretty sure, but we do not know the size of non-Gaussianity in the ekpyrotic phase. So this is pretty similar to gravitational waves. That for gravitational waves, you know, so there is a characteristic blue spectrum, but the size is too small. So you cannot actually compare inflation and ekpyrotic in this kind of basis. So here, actually, this is a well-defined problem, but we just haven't calculated the size of non-Gaussianity here.
Thank you. More questions? Daniel?
A question about your comment that it's similar to gravitational waves, because as you explained, if the interactions are gravitational, we expect gravitational interactions to be there at a minimal level. So if you could measure those things, you would have to see something. Those particles exist. That makes it slightly better.
Right. First, from my own interest, I should not say anything against you. Yeah, but there is the assumption that we have the massive fields. Yeah, this is natural, but this is not guaranteed.
Sure. Yeah, if that's what you meant. Okay.
Yeah, so that could be exponentially surprised.
Okay, good.
Another question here? Well, if not, let's thank Yuan again. The next speaker is Marco Peloso, and the talk is about signatures of particle production during inflation.
This? Okay? Okay, thank you. So many thanks to the organizer for the invitation and for putting up this very nice conference. And I'm going to talk about a series of works with several collaborators in the past few years about the particle production in models of axion inflation. So we know one issue of models of inflation is to keep the potential flat against radiative corrections. And we usually use symmetries. For example, a shift symmetry could help in this way. In a sense, you can have coupling of the inflaton to matter, which are shift symmetric. And so these couplings by themselves don't modify the inflaton potential. Now, what does this buy? Well, the smallness of the inflaton potential is technically naturally guaranteed in the sense that you need to pay a price proportional to the potential in any loop that modifies the potential. Moreover, this gives predictivity better than usual models of inflation because at least the couplings are highly constrained. There has been a lot of discussion on whether these models are consistent with quantum gravity, and this is not easy, and I don't really have much to say in my talk. So I'm going to just assume a given potential, and I'm using a phenomenological approach where I will discuss the limits and the possible signatures arising from this coupling. However, I want to acknowledge that this is a problem and there is work that is done in this area. So one possibility is to couple two fermions. This is something that we studied recently. I don't really have time to discuss it in my talk. And I will focus all my talk in the couplings to vector fields. And this is the typical pseudoscalar couple to FF tilde. And this modifies the equation of motion of the inflaton field, of the vector field. And you can see the presence of the last term, which is proportional to the speed of the inflaton. And the last term, you can see it has different signs for different helicities. And in particular, one helicity becomes tachyonic at some regime after horizon crossing. If this parameter xi is of order 1, you can see that essentially here is the energy density in one single mode as a function of scale. Inside the horizon, you renormalize this away. This is the usual k-square contribution. And then you will get that there is an amplitude that is due to the field amplification, due to this new term. And eventually, the expansion of the universe dilutes it away. So this thing is regulated in infrared. But in the meantime, you get an amplitude that is proportional exponentially to this parameter psi. The perturbations that we studied long ago, you can produce a perturbation of the inflaton field just from inverse decay, or you can produce gravitational waves. Now, this is the result that we got for taking very simple monomial potential, like, for example, a linear scale, like in monodromy. And you can see as a function of the production parameter, you can get large non-Gaussianity, is nearly equilateral type. And by respecting the Planck bound, we have a limit on the axion scale. Or we can get the tensor to scalar ratio, because of course you can also produce gravity waves. What is very interesting to notice from the second panel is that the more production you have, the smaller tensor to scalar ratio is. Because essentially the crucial point is this term here at the denominator that is produced more strongly than gravitational wave. And actually it's a general message that I want to give, that you know, there is a lot of study. People are really putting a lot of experimental effort in determining the B modes, the gravitational wave on the CMB. And because there is a nice relation to the scale of inflation. The question is, right, suppose that we observe the B mode in the CMB, are we really sure that we are testing this relation, or can there be some way out? And there's been a lot of activity in the literature of people that propose models that give additional gravitational wave. However, the difficulty that you really need to keep in mind is that it's not enough to just compute this term here. You also have to compute this term here. So many papers, they claim that they produce more gravity waves, but in reality they decrease the tensor to scalar ratio if you do the full calculation. And this is an example where you really need to compute also the scalar perturbation to give the full message. So now over the years we came out with some conditions. They are not mandatory, but they are conditions that help to increase the source tensor perturbations versus the source scalar perturbations. You would like, for example, if you don't have direct coupling with the inflaton, it's better, because then you produce as little as possible scalar perturbations. You want to produce a relativistic source, because the gravity waves are sourced by the quadrupole moment. So if you produce something non-relativistic, it will produce very little gravity waves. And also, it could be interesting to have the source active only for a limited amount of time. Because if you do so, you modify fewer modes, and so you decrease the limit from non-Gaussianity. Of course, it's a very highly tuned idea, because you modify only the scales where you probe the gravity waves, and you minimize the limit from non-Gaussianity by not modifying smaller scales. Just to show that this can be done, we cooked up a very toy model, where here there is an inflationary sector, which is only gravitationally coupled to the sector with the pseudoscalar couples to FF2. And we choose the simplest potential term for the pseudoscalar. But the important point is that we tune the mass of the pseudoscalar to be comparable with H, so that the rolling of the pseudoscalar only takes place for a few number of epochs during inflation. Then we do the calculation of all perturbations. At the end of the day, we are interested in perturbation of the inflaton and in gravitational waves, which are both coupled only gravitationally to the sector of particle production. And it's possible to get it's possible to get observable gravity waves at arbitrary small scale of inflation. Here is some existency proof. So we choose epsilon parameter 10 to the minus 5, so that the vacuum perturbations are non-observable. And here is the change in the scalar perturbations, how it modified TT correlators. We choose bumps which are compatible with 2 sigma with the data. And now you can see that you can be compatible with 2 sigma, but you can generate large bump in BB. Different colors correspond to different choice of parameter when essentially the inflaton is going to roll. And as comparison, I'm showing the scale invariant signal in dashed line, 10 to the minus 1, 10 to the minus 2, 10 to the minus 3. And you can see that in principle it's possible to probe this model by the shape dependence, because there's a very different shape. Of course, this means that we need to measure gravity waves in a sufficiently large window. Another possibility is that this has a BBB correlation function, so this is very strongly non-Gaussian. And it has been shown, for example, that you can test this on a satellite like LightBird. The moral is that it's hard to violate the standard conditions of inflation. And here I gave you an existency proof where really I follow a set of rules in order to maximize it. And it's not very easy, which is good because it means that there is some robustness in the standard prediction. But in principle, you can do it, and you can do it in a way that can be probed, at least in this type of models. Let me now go back to the possibility of phi being the inflaton field. And we remember that this coupling is proportional to phi dot, and phi dot grows during inflation. So this naturally gives us a framework where we can have naturally blue signals, right? The signal is going to increase a late time where you're looking at small modes. And something right that we all know, but we don't always say it, is that from the CMB we only measure a very narrow window of inflation, even if we add CMB distortion. And there is a large potential window which is too small to affect the CMB. And how can we probe inflation in this range? Usually the gravity waves are too small to be observable, but here we have a mechanism that naturally produces larger gravity waves at smaller scales. And so, for example, these new experiments that are being built, they can really open new windows to probe later times of inflation if you have a signal that is sufficiently blue. And I'm going to focus on LISA 3-satellite constellation, which is going to be launched in 2034, hopefully. At least this has been approved. It has nominal duration 4 years, but it may last for up to 10 years. And here we studied, it was just a simple exercise, to do this signal as compared to LISA. You can see that here is very small amount of gravity waves. This is the vacuum signal. But then the source signal takes over, and it is blue. And in principle, you can be inside the LISA band. Now, different bands here corresponds to different configurations, different length and different duration. Now, what has been approved is essentially the middle one. Now, the question that we can ask is the following. LISA, we know, will observe a stochastic gravitational wave background, but how can we really know that it is from inflation? How can we not know that it's not astrophysical? And there are some properties that this production has, which in principle are very characteristic, and they are not present for astrophysical signal. One is parity violation. The signal, you produce more gravity waves of one chirality than the other, but you cannot measure with a planar instrument violation of parity. But then there is non-Gaussianity. And in principle, this can be measured by ground-based interferometer, by interferometer, also LIGO or LISA. And here is the example of LISA, and we studied it in this work. You know, there are 3 vertices, so these are 3 time delay interferometers. But these interferometers have one arm in common, so the noise is not orthogonal. But you can diagonalize the noise matrix, and these are the channels that diagonalize the noise matrix. And essentially, people have computed the 2-point response function. So what is the 2-point response function? Signal square is the response function times gravitational wave square. This is proportional to the energy in the gravity waves. So that's why people have studied the 2-point function. However, like we now do with the CMB, why shouldn't we study the 3-point function, right? The crucial point is that astrophysical sources, due to the central limit theorem, they are expected to produce a stochastic Gaussian background. So how can we hope to see something from inflation? By looking at the higher order correlators. And that's actually what we studied in this paper. So this is something that I don't see that been done in the literature, but I think is very nice, and the data are going to be there. So this is for free, and we can just study. So this is just the frequency dependence, and this is the response function. Now, there are only 2 non-vanishing correlators due to some symmetry. This is very highly symmetric. And they are also predicted to be one the opposite to the other. Here is the response function of gravity waves of the same chirality. Due to parity invariance, response to left, left, left is the same as response to right, right, right. And here is the response function of gravity waves of 2 left and 1 right, or vice versa. So this is not only for axion inflation. Any model that gives gravity wave from inflation that can be expected to have large non-Gaussianity can be probed, and this would be LISA, but you can also probe it in ground-based experiments. So A and E are, you see, Sx is the time delay at this vertex, X, Y, Z, Z are the time delay at this vertex, but these vertices have one arm in common, so the noise is not orthogonal. So you can take linear combination of them that makes the noise orthogonal. You see, I define it because we are not used to that, but people at LISA, they know. This is the H called H channel, E channel. The important thing is that they are noise orthogonal. But they're just linear combination of the delay at the vertices. Now, even in this case, we need to play scalar perturbations versus gravity waves. And if you look at the models of chaotic inflation, where you have a standard potential, like in chaotic inflation, the primordial black hole limit prevents gravity waves from being observable at LISA. This is essentially a limit not to overproduce too many scalar perturbations at small scales. However, we need to see that the limit here is determined by the smallest possible primordial black holes that you can produce, n is equal 10. Primordial black holes that are produced later evaporate before BBN, so the limit essentially disappears. And so here is the limit that you can get for a blue signal, but then you can see that this limit is very different from the range that you're probing at LISA. And the crucial point is that in order to get such a statement, you really need to specify an inflaton potential. And the primordial black hole at LISA's case do not prevent gravitational waves from being observed at LISA. Just to make a simple existence proof, this is really a toy example. I don't think this is serious, but it's just to show one example. I just modified the slope of the inflaton potential by a factor of 3, and the signal changes by many orders of magnitude because it's exponentially sensitive to the speed of the inflaton. So here you can see you can respect the primordial black hole limit and have a signal observable at LISA. What I'm really trying to stress is that these are new windows on inflation, and we, as much as we use the CMB to probe inflation at n is equal 60 or 50 or whatever, we should use these experiments to probe the inflaton potential at different values. And in an agnostic way, I think is the best way when we have an experiment. So in the final part of my talk, I want to discuss a different model, which is a chromonatural inflation, but I will want to show that similar considerations apply to this model. So the basic idea is the old idea of worm inflation, where you have slow roll from particle production. There was a gauge field realization by Amber and Sorbonne in U1 case, and then Ashed and Baumann did SU2 realization. But what is really new in this realization is not just the SU2, but the fact that the vector fields have theta. And you see the Lagrangian is very similar to the one I'm discussing with this term. And there is a vacuum expectation value for the gauge fields which are arranged to be isotropic. You see there is a locking between SU2 index and space index. Doesn't really need to be so, but if you do so, you have isotropic expansion. So this parameter Q is represents a VEV that evolves in slow roll, and chi is the inflaton field. Now this model needs very large values of lambda here to have sufficiently production to have a slow roll. And this is not easy to achieve, and this was emphasized in a very nice paper by Matthew and collaborators, and I'll recommend you to look there if you want to see discussion of this issue. But here, let me take this at face value, and let me study the perturbation from this term. Also because these effects here will apply to many models that have common things as chromonatural inflation. So you will see, we will see in the next slides, that perturbations are mostly controlled by this parameter. This is the ratio between the SU2 mass of the vector fields and a Hubble parameter. And you can show that you have a slow roll evolution like this. So you can see that when MQ is greater than 1, essentially the parameter that we call psi in the previous slide is equal to MQ. What I want to stress is that there are a lot of things that we learn from the U1 case that can be somehow translated to this case here. And I don't want to be too technical, but essentially from the vector field, there are 6 new physical modes. You eliminate 3 by gauge choice. 3 of them are non-dynamical, so you end up having from the SU2 multiplet 6 new modes. 2 of them mix at the linear level with the inflaton and scalar perturbation, so we call them scalars. 2 of them we call them vector. 2 of them mix with the gravity waves, so we call them tensor. And it has been shown the phenomenology of this model is ruled out, actually, so the simplest implementation. So here I'm showing the usual NSR plane. Different colors are different values of lambda. Different symbols are different values of this combination, which relates to the parameter MQ. And notice, as I was telling you before, that the choice of parameters that have same MQ give a very similar result. So the phenomenology of this model is mostly controlled by this parameter MQ. Now, in order to, since this is ruled out, people discuss different implementation of this model. For example, here is done for a cosine potential. You can cook up potential and not, well, you can make models where this potential allows to get better agreement. You can have models which have multiple fields, axion different from inflation, spontaneous broken SU2. There is a list of people that have worked out modification of this model to get agreement with observations. Now, what is an interesting feature from the phenomenology of this model is the gravity wave sector. And let's remember that I was telling you there are 2 extra modes that come from the SU2 multiplet that mix with gravity waves. And one of these 2 modes has a tachyonic enhancement, is the counterpart of what we have in the U1 case. So you can see here, right, when you are outside of the horizon, there's nothing, but when you are getting close to the horizon, you get this tachyonic growth, and which will then disappear. And the magnitude of this production is exponentially sensitive to the parameter MQ. So you see, this is very similar to what I showed you before in the U1 case. And people have studied the new gravity waves that appear due to the linear mixing between gravity wave and this mode. And in particular, we are going to hear, I believe, in next talk by Eiichiro, how you can get a very interesting non-Gaussian signal. The SU2 structure gives natural interactions that will eventually give a non-Gaussianity of this background, which is something that experimentally is very interesting. And however, what we have done in the last paper, again, let's remember what is the main motive of this talk. Let's compute gravity waves, but let's also compute scalar perturbation, because the 2 need to be studied together. And as much as people have studied how this mode sources gravity waves, now I want to study how this mode sources scalar perturbations. This is something that has been done only very recently. And the computation that we have done only applies to the chromonatural inflation model. So the numbers that you will see next don't apply to the model that Eiichiro is going to discuss in the next talk. But the physical effect will also be present there. So it's just a matter of quantify it. But the features is here. We have done it for the simplest original model, and now, right now, we are trying to work it out for more generic models. So here is the result. So I'm showing the ratio between source scalar perturbation versus the linear perturbations. This is different values of the axion scale, f over m Planck 10 to the minus 2 or 10 to the minus 1. Different colors are different values of lambda, and different shapes are different values of MQ. And you can again see, really, that this effect here is only sensitive to MQ, essentially. This again tells you that MQ really controls the phenomenology of this model. And we have some semi-analytic approximation. This is not easy to do this calculation, but there is things that can be done analytically. Probably the simplest thing to see is that there are 2 powers of vector fields. So when you compute power spectrum, there's going to be 4 powers of TL. And remember that the production was e to the pi MQ divided by 2. So there are 4 modes that give this dependence. And then there is this complicated power law that can be understood somewhat semi-analytically. So now this is the main, I'm going to show you the main result, and then I'm done. So this is the result I just discussed with you. And now I want to stress that as in the U1 case, this parameter MQ is growing during inflation. Because n is going to 0, this is just the fact that the inflaton is speeding up. So again, particle production is becoming stronger and stronger. So now, first you can get some interesting positive message. Because essentially, remember that the power spectrum was too red. This was the prediction of the linear theory. It was possible to get a small enough R, but the power spectrum was too red. Now you have a new contribution, which is blue. And so in principle, this can be improved with observations. So this is the linear result. Now for these two cases, the particle production is so small that the linear result agree with, this is negligible. But then for this case, just adding this term brings you from year to year. So now you can see that the full curve will be in better agreement with the data. I'm not claiming agreement with the data, I'm just saying that this will improve. Also, I didn't study non-Gaussianity, so it may be that this is already ruled out by non-Gaussianity. But at least there is a blue tendency, which will improve CMB comparison. However, really what is really interesting to study is what's going to happen at smaller scales, as in the U1 case. Because now, this is how the ratio behaves as a function of number of e-folds. I'm assuming inflation is 6 e-folds for different values of this parameter at CMB scales. And you can see that this ratio grows just because this parameter MQ is growing during inflation. So you should worry about what about possibility of producing maybe too many primordial black holes, what about limits from perturbativity. These are things that we discussed in the U1 case, and now we have the tool to discuss these things also in the SU2 case. So let me conclude. Here I really try to do a phenomenological approach. I just took a coupling during inflation, and I discuss what are the possible signatures. But what I try to really be concrete is to compute both gravity waves and scalar perturbations, because these two things need to be computed together to get the full picture. We show that it is hard, although it's not impossible, to modify gravitational waves at CMB scales. We show that in principle the model is naturally blue, the mechanism, so you can produce things at smaller scales, which will probe later stages of inflation. And also, as much as we study the U1 case, we have also studied the SU2 case, but there is current effort to work out all the details also for these non-abelian models. Okay, thank you for your attention.
Thank you, Marco. Questions? Please.
Hi. On the plot with the LISA and LIGO power spectral densities, you had a few for LISA, which is fine, I understand why, but you also had a few for LIGOs. Can you say what they represent? Is it just the evolution over the next few years, or what?
Yes. No, I don't.
Next one, I think.
Sorry.
Yeah.
I don't remember anymore. These are various versions of advanced LIGO. I believe that's where we stand, and that's where we are going to go in the next few years. In the paper, we really write what each curve corresponds to, but I don't remember right now. But yes, it's the improvement of advanced LIGO in the next few years. Thank you.
More questions?
Yeah, maybe just a small confusion. So about the case where there was a second field, not the inflaton, that was producing the axion, in what sense do you call one the inflaton and the other one not? Is it not a linear combination of the two?
No, it is a linear combination of the two, but the sense is that this guy gives a much subdominant contribution to the inflationary expansion. So when we do the calculation, yes, you need to diagonalize and do it properly. But the main idea is that we impose conditions where this is dominant, and this is what plays the role of more spectator fields, and its role is just to transfer perturbations to the phi.
But when you say it's dominant, if it's nearly constant, I have a hard time actually. You could also move it to V of sigma, so I'm a little bit confused. In what sense is it dominant?
So these will dominate the energy density of inflation, and at late time it also dominates reheating. So that's where the one that you would normally call the inflaton, and this would be called a second.
Okay, let's thank Marco again. we reconvene at 11?
Okay, let us start the second session of morning. And the first speaker is Eiichiro Komatsu, and the title is Non-Gaussian Gravitational Waves from Inflation. Please.
안녕하세요. So let me continue on the gravitational waves from gauge fields that Marco already started talking about. And by the way, so thank you very much for organizers. I always enjoy visiting Korea. I love bibimbap, ugoji kalbitan, all these nice things. I have only 3 dinners, and I have to use them very wisely to eat what I want to eat. So that's a major challenge. So let me first show this power spectra of the cosmic microwave background. So what you see here is the temperature from top to bottom, the temperature power spectrum coming from scalar perturbations, namely sound waves and gravitational potentials. Then the middle one is the E-mode polarization power spectrum coming from the sound waves as well. Then what you see in the bottom are 2 curves. One here is the B-mode polarization power spectrum coming from the primordial gravitational waves, getting invariant with the tensor to scalar ratio of 5%. Then what you show here in the dashed line is the B-mode polarization coming from the gravitational waves, the gravitational lensing. And what you can see here is that all but this tensor gravitational waves has been detected. And then they are in wonderful agreement with the standard prediction of the lambda CDM cosmology. In fact, you don't even have to fit to these data points. You can fit everything only to the temperature power spectrum and predict what this E-mode sound wave and also B-mode gravitational lens would be, and just plot theory on top of data points and they'll go right through. So this is the amazing confirmation of our knowledge of the current universe. But we don't want to stop here. We want to measure this and complete the measurements and interpretation of the cosmic microwave background. So this is in power, and you see that from the very first detection of cosmic microwave background anisotropy at L equals 2 by Kobe in 1992. It took only 25 years to go from here to here. 7 orders of magnitude in power. But we don't want to stop here. We want to improve another 2 orders of magnitude at least in the next 10 to 15 years, and hopefully we will get down there. All right, so the key predictions you already heard, excellent talks by 3 speakers in the morning, what the inflation would predict. So first they predict scalar perturbations, zeta. They also produce tensor perturbations, Hij. And we want to measure those things. So these are metric perturbations. You have the scale factor that gives you the overall stretching of the distance between 2 points in space. Zeta will give you the distortion to the determinant of the metric, determinant of the distance between 2 points. This Hij will give you the anisotropic area conserving distortion in the distances between 2 points. And we want to measure this thing. How do we do that? So you all heard about LIGO. You will also hear about LIGO and LISA later in this conference. So distance between 2 points will be distorted in anisotropic area conserving way. So you put 2 mirrors like that. You have a beam splitter, and then you shoot laser from the left, split into 2, and then, but when you split, you give you the phase shift to 1 laser beam, so that when they come back and combined, crest and trough of the laser signals will be canceled, and there is no signal. That's your initial configuration. When gravitational waves pass through, there will be a geodesic deviation, and then that will give you the change in the relative distances between these 2 mirrors, geodesic deviation, and then you see the signal. So that's the idea. But the way the LIGO detected this, and Lisa will do similar thing, not quite the same, but similar. You can detect gravitation waves with wavelengths of about size of the Earth, because it's a ground-based detector. For Lisa, it will be a much greater wavelengths, longer wavelengths, but only a few thousand kilometers from the LIGO. But primordial gravitation waves coming from inflation was stretched by enormous cosmic expansion to something like billions of light years. So you can't possibly use laser interferometer approach to detect the gravitational waves coming from inflation that are relevant to cosmic microwave background experiments. So what do you do? So we use universe as a detector. You have isotropic electromagnetic fields, and you put, so isotropic electromagnetic fields will be basically cosmic microwave background, 2.7 Kelvin everywhere. Then you let gravitational wave pass through. So let's call this plus mode, call that cross mode. They stretch space, and they stretch wavelengths of light as well. And when wavelengths of the light is stretched, energy goes down. Therefore, you get cold when the wavelength is stretched, and hot when wavelength is scorched. So this will generate temperature anisotropies. Moreover, when you put electrons here, then imagine that photons coming from this direction get scattered by electron and coming toward you. Okay? So now you have to pretend that you saw electrons and temperatures around them, and temperatures around them were scattered by electrons coming toward you. And how would that light look? They would look polarized. So when you have this anisotropic radiation field, let's say hot here, and cold here, you get this horizontal polarization. Why is that? How do we know that? We know that from the daily experiences. So when you have the car with windshield and sunlight is coming from above, so you have this anisotropic incident light coming only from the above, then this light is scattered by windshield and coming toward you. And it's actually horizontally polarized. And how do you know that? So you go to this company Talex and ask for these polarized sunglasses, which you block light that's horizontally polarized, and you transmit light that's vertically polarized, and you can see through the car. Okay? So we basically do the same thing to the universe and try to detect polarization of the cosmic microwave background. And we'll then claim, for example, that important thing is that gravitation waves have these two polarization states, linear polarization, plus and cross. And whenever you have, so of course, what's plus and what's cross depends on coordinates. When you tilt your head by 45 degrees, one gets to the other. But the fact that these two things coexist is coordinate independent. Whenever you see horizontal polarization, it has to be accompanied by 45-degree tilted one. That's the signature. And that's the signature we're looking for. We haven't detected it yet, but we're working on it. All right. So the standard law is that when you have gravitation waves in vacuum, right? So there's nothing on the right-hand side of the wave equation. You quantize this and compute the power spectrum, you get this famous formula, namely the power spectrum of gravitational waves is proportional to Hubble square. And because Hubble is nearly timely independent, this will give you the almost scale invariant power spectrum of the gravitational waves. Great. But, so at the production in a very early universe, this thing is scale invariant. Now, as gravitational waves propagate throughout the universe and come toward us, and come toward our detector on Earth, or anything else that you can think about, their spectrum is modified, and they look like that. Now, this is the energy density spectrum of gravitational waves. Goes down like 1 over frequency squared. Then the approach is nearly constant. All these bumps and wiggles are very interesting features. If you wanted to know anything about this, ask Yuki Watanabe, who is in the audience here. But this is the kind of standard law spectrum of gravitational waves, nearly scaling invariant, coming from vacuum fluctuation in the metric perturbation during inflation. And the wavelengths of gravitational waves that corresponds to CMBs, billions of light years. Pulsar timing array is here, and interferometers are here. So in principle, as Marco emphasized, you can get really a great spectroscopy of the gravitational waves if you can measure gravitational waves here, here, and there. Okay? But wait a minute. If you go to the math class and you are asked to solve differential equation, and then just automatically assume that there's no inhomogeneous solution. You just automatically set right-hand side to be 0 and never talk about it, you fail. So why are we not talking about this? And well, there's no really particular reason why we shouldn't be talking about it. We should be talking about it. But as Marco emphasized, it's not that easy to produce gravitational waves from the matter sources for various reasons. For example, when the background spacetime is homogeneous and isotropic, there's a theorem saying that tensor and scatter and vectors are completely decoupled. They do not influence each other at the linear level. Therefore, if you had a scalar matter fields, you have to go to the second order to produce gravitational waves. But at the second order, there would be curvature perturbation over the similar amplitude. Therefore, you screw up scalar perturbation when you try to produce tensor perturbations, as Marco emphasized. Vector is the same story. You have to go to the second order, and the second order producing tensor perturbations will produce scalar, and you screw up everything. But if you go to SU2, story is completely different. There, I will get there later, okay? But I wanted to tell you, okay, and this is sort of telling myself like a few years ago, okay? Many people in the CME community, especially people who are making measurements, took for granted for many years that the detection of B-mode polarization in the CMB from gravitational waves will be the smoking gun for quantum vacuum fluctuation in the metric. Okay? No matter source whatsoever. We didn't even talk about it before. We didn't think about it before. That was the kind of standard thing that everybody would write in like grant proposals and got money. No, we shouldn't be doing it. Okay? That would be that wouldn't be honest, right? So and that gives you many more exciting opportunities. It's not just homogeneous solution. You have to talk about inhomogeneous solution, and that this will give you greater scientific possibilities. So experimental strategy commonly assumed so far, including myself, for many years in the past, we wanted to detect the B-mode polarization in the gravitational waves, and then we check that it has the black body spectrum, so that it's actually CMB, not thermal dust. Second thing is check for scaling variance, and because inflation predicts that it has to be scaling invariant. And if it's yes, we have some kind of press release or whatever, and then claim a victory. We found inflation. If not, we scratch our head and say, maybe it's dust, maybe it's something else. But now, if you have the source contribution, it's not necessarily scaling invariant. It's not necessarily Gaussian. It's not necessarily parity conserving. Therefore, you have to not only check for scaling invariance, but also parity violation and Gaussianity. And only if it's scaling invariant, Gaussian, and parity conserving, you claim a victory. Okay? If not, it could be even more exciting, right? So you just found new physics during inflation. It's not just semi-boring vacuum fluctuation in the metric. But then people say, oh, cool, well, I don't want to hear about sources. Just want to live with vacuum. Well, but I mean, you have to be fair, right? So these matter sources are there for sure. And you heard 2 talks in the morning. It's completely natural to have extra sources, extra fields during inflation. They are subdominant in terms of energy density to the inflaton field, but their energy densities can be quite significant to produce sizable gravitational waves. After all, gravitational waves' energy density is small anyway. And producing gravitational waves with a sizable tensor to scalar ratio from the vacuum is a challenge. Because in order to produce R that's much greater than 10 to the minus 3 will require typically the excursion of the fields, inflaton field that's bigger than Planck. And there are many reasons to hate that. But if you have a source, you don't have to worry about this in principle. So you can have completely valid phenomenology. Field excursion is sub-Planckian, but still detectable gravitational waves. And because it's particle physics, you can connect this. For example, when you have chiral gravitational waves, they can give you baryon number by gravitational anomaly. And so on. Then you can connect this gauge fields to reheating. You have many more things to probe within this framework, and that's why this setup is quite attractive. And I'm only new to this field lately. These guys converted me into believing in this. So you already heard about from Marco a nice review on this scenario. So let me just jump into this the model. So here it's a slightly different configuration from Marco's talk. So I have Einstein-Hilbert action and inflaton sector, which I do not want to talk about. I don't know. I don't understand inflation. Probably no one understands inflation. I don't want to talk about it. Okay. It's just, it will give me quasi-Daejeon background. On that, we have this pseudo-scalar axion, spectator, namely, it has a negligible contribution to the energy density. They just play happily in Daejeon background. And I have also the SU2 gauge fields, which are happily being spectator, and then axion will pump energy into the gauge fields so that the gauge fields wouldn't just decay as a radiation, but they do something else. Now, so it's a very well-defined setup. Yes, axion SU2 gauge field dynamics is in a given Daejeon background. It's a very nice playground for particle physicists. Everything is calculable. And let me emphasize that the very first person to realize that SU2 is unique is Azadeh Malek-Nejad. When she was a graduate student in IPM in Iran, she discovered that you can get inflation out of gauge fields, that's the first thing. But another thing is that in this inflating background, SU2 gauge fields acquires vacuum expectation value that's isotropic. It's a major discovery. And it's really due to her. So Marco showed this already. So you have this gauge field. This SU2 index is now identified with the spatial index, namely the SU2 gauge field is configured in such a way that it respects isotropy. It's simply because SU2 is isomorphic to SU3, so it can actually give you the isotropic solution. But not only that, this is an attractor. So it's not put in by hand. It's something that emerges. In this configuration, you can show that the perturbations on top of the background have spin 2 degrees of freedom. It has also scalar and vector, but it also has spin 2 degrees of freedom, despite that the SU2 gauge field is a spin 1. But the perturbations actually behave as if they were spin 2, namely they transform like spin 2 under the spatial rotation. That's a very interesting discovery too, due to her. Now, and then, so thanks to that coupling, this Chern-Simon coupling FF dual times axion, you can produce spin 2 fields that are chiral. So only one helicity gets amplified. Therefore, you get this completely chiral gravitational waves that you heard already from Marco. And then this SU2 fields has self interaction, which is completely absent in abelian gauge fields. Due to this self-coupling, you have a very large 3-point function. which is a unique signature of this SU2. So let's look at this phenomenology. So let me define this canonically normalized gravitational waves by basically multiplying that by scale factor times Planck. Then you have this psi equals 0. That will be the vacuum equation. But as promised, due to the presence of SU2, now you have source terms. These T's are the spin 2 fields. These two spin 2 fields obey its own equation of motion, and it has a mass. So these are massive spin 2 particles. But this mass can become negative for one of mass squared can become negative for one of the helicity states. So one of the helicity states can get exponentially amplified near horizon crossing, but after horizon crossing, they decay because they become massive. All right, so let's solve this equation ignoring the right-hand side, because right-hand side is like, so first of all, this spin 2 fields linearly mix with gravitational waves, producing gravitational waves. These gravitational waves will then back react on the spin 2. Let's ignore that back reaction. Let's just look at spin 2 first, ignoring right-hand side. Then this has an analytic solution that's Whittaker function, written like that. Plug this into the right-hand side of the Einstein's equation. Then you get inhomogeneous solution, not the vacuum solution, inhomogeneous solution for these gravitational waves. And power spectrum would be written like h squared divided by m Planck squared, just like the vacuum part, times this exponential factor, which can be huge. And this epsilon is some small number, like something like 10 to the minus 2 or 10 to the minus 3 or 10 to the minus 4. But this exponential factor easily compensates for it, producing source of gravitational waves much bigger than vacuum. So that's a new paradigm. And the phenomenology, Marco touched on this already, that this negative mass square term can grow as field rolls faster near the end of the inflation. Hence, you can get not only the CMB, but also LISA and BBO. These interferometric observations can be sensitive to the gravitational waves coming from the SU2 gauge fields. So it's very nice. And tensor spectra could be scaling invariant. They don't have to be. So this is something you can check. And indeed, for these kind of bumpy gravitational wave spectra, you can get pretty harmless BB, CMB power spectra, but they are in fact not scaling invariant. So you can fit spectra, you can reconstruct spectra from this and see whether they look like scaling invariant or not, right? So that's one signature. Another signature is that because it's parity viral, it's completely chiral, T and B are correlated, E and B are correlated as well. So this is a TB and EB. But this kind of TB correlation, EB correlation can be created if you don't know your detectors either. So you have detectors which are sensitive to polarization this way, but you didn't know that. Actually, polarizations, detectors are aligned in that way, then polarization in the sky will be uniformly rotated. This will convert E to B in a uniform way, and this will convert, this will produce TB and EB, which will look like TE of the scalar and EE of the scalar multiplied by some factor. That will be this. So this is the TE of scalar multiplied by some factor. This is coming from TB of the angle miscalculation. But this TB is completely different. This TB is not scalar. This is tensor, whose shape is completely different from scalar. Therefore, you can easily distinguish between them, easily. So this is something you can actually do even if you didn't know your detectors well. So that's super exciting. And finally, it produces large bispectrum. So the convenient quantity to quantify the magnitude of three-point function is the three-point function divided by the two-point function squared. For equilateral configuration where all the k's are the same, standard vacuum single field inflation will give you this vacuum fluctuation, which will give you this quantity that's 3.9. Here, it's much, much bigger. This omega A is the energy fraction in gauge fields. Because it's spectator, this can be as low as 10 to the minus 5 or something. So it's a huge number. So huge that this indicates that your perturbation calculation is breaking down. So eventually you have to do something like lattice simulation, which we are doing at the moment. But this offers a very powerful test of whether the detected gravitational waves come from the vacuum or sources. And so this is a cubic Lagrangian from which you can calculate second order equation motion. You solve for second order equation motion, you then try to calculate bispectrum as linear times second order, which will give you the non-zero bispectrum. Then you can, and because of this self-coupling, this bispectrum is not produced at the loop, it's produced at the tree level. And that's why you can get large non-Gaussian in tensor, but still small, relatively small contribution in scalar. Result is that, so this corresponds to the equilateral triangle, this corresponds to the squeeze triangle, this corresponds to the elongated triangle, and this looks more or less equilateral, but not precisely, and for the reasons we look at this paper, this explains why this shape looks the way it does. So it's very unique signature which you can look for in the data. For example, you might be worried about foreground emission, thermal dust, synchrotron. They wouldn't look like this, right? So I am sure that we can distinguish between non-Gaussianity coming from foreground emission and non-Gaussianity coming from gravitational waves. We've done that for scalar, so I'm sure we can do that for tensor as well. There is a limit already on tensor non-Gaussianity, although tensor has never been detected. You can assume that everything you saw in the temperature anisotropy is coming from the all the non-Gaussianity in the CMB temperature would come from tensor perturbations, and you try to limit the amount of tensor non-Gaussianity you allow from the temperature. And it's, for this kind of funny-looking quantity, it's 400 plus minus 1500. There's no evidence for non-Gaussianity in tensor or scalar. And our model predicts something like 3 times r squared over omega a. So clearly, this can be much bigger than this. So current data are already constraining SU2 gauge field. And in the future observations, we can go to FNL over few. So we improve constraint by factor of 1,000 already with the future data, but not so future. In fact, I think, so this is for satellite emission, but I think the satellite emission that I briefly touched on because I'm running out of time, full sky light bird, right? The noise level expected for light bird is already sort of similar to noise level already achieved for BICEP, ground-based. But BICEP measures 1% of the sky, not full sky. So that you can just scale this to 1% of the sky. So you multiply this by 10, and you have a few tens, not few, but few tens is 100 times better than 1500. Therefore, you already, I think, improve on the constraint by factor of 100 using existing BICEP data. So if there's a BICEP people in the audience, I'm sure there is, I want to talk to you. Okay. So then, in the end, you can do parameter scan. So these are 2 parameters. This is basic energy density fraction in the gauge fields. This is MQ. That's this coupling times vacuum expectation value of the gauge field divided by Hubble. And then this is the limit coming from the tensor power spectrum. This is the limit coming from the tensor bispectrum. These are limits coming from various other things. And then this is the parameter space that's still open. And you can improve upon these constraints by having better measurement of bispectrum, better measurement of power spectrum, and so forth. Now, now you have the, but wait a minute, okay? Is this really viable? So you have this background gauge field, which is rather strong. Didn't Schwinger tell us that whenever something like that happens, you have pair creation of charged fields, charged particles, which will destroy the background gauge fields, like a Schwinger effect? When you have a very strong background electromagnetic fields. Wouldn't then pair create positron and electrons, which then extinguish the fields? String effect. How about string effect? So we computed that, and it turns out that this is not important. And I don't have time to explain why, but it's not important. So that's good. So this phenomenology works quite well. And Marco emphasized that we should also look at contribution to zeta. I'm also done. So we have zeta contribution coming from the inflaton, spectator axion, spectator gauge fields. Long story short, these two terms are not important. So what you have to worry about is the production of chi coming from gauge fields. Chi then produces phi, and phi produces zeta in this way. Okay? And Marco already showed that this A to chi is very efficient, and this is huge. But in this spectator model, you have one extra step that go from chi to phi. And because phi and chi are only gravitationally coupled, there's an extra suppression of 10 to the minus 12. And then the end result is that this means that the curvature perturbation coming from gauge fields is less than 1% of the vacuum contribution. So within this framework, at least, power spectrum level, everything is fine. And I wanted to tell you about Lightbird, but I don't know how much time. Just to tell you that we are in the last round of being selected or not by JAXA, this Japanese space agency, to launch this next generation polarization satellite called Lightbird. And if we are selected, we'll go in 2027. And target is number 3 in R. So let me skip all that. It broke. Yeah. Then let me summarize that with Lightbird, we want to reach R of 10 to the minus 3. But really the exciting question is whether these tensor modes are coming from vacuum or not. And either way, we'll learn a great deal about the inflation. Thank you.
Okay, any question? Please use microphone.
So as a Marco and you including the SU2 coupling to the pseudoscalar.
Yes.
So in that case, you should also consider the U1 coupling to the FF tilde U1 to the axion or any others.
Mm-hmm.
Then you will naturally have the bifringence. And then
yes,
they will naturally give you the pseudo B mode amplitude. So when you count the B mode contribution from the inflaton, in addition to that, the polarization plane from rotation plane from the bifringence, naturally we should have a confusion. We cannot separate the R.
We can. That's exactly what I said. So, but I was.
That's from the SU2.
No. Let me. You're completely right, and I was going too fast. Okay, and in fact, when I showed this, I only talked about detector miscalibration, but this is bifringence. So when you have the electromagnetic waves coming, and you have the pseudoscalar rotating the polarization direction, right? That's this. It's exactly the same effect. Right. But this gravitational wave bifringence, it's not really bifringence, gravitational wave TB is completely different shape. So there's no confusion.
So in addition to this, because this is come from SU2 tensor mode.
But this is bifringence. This black line is bifringence.
You mean the U1?
Yes, the U1 or anything. Yeah, so this is bifringence. This is a uniform rotation. So as you can see, bifringence effect is completely distinguishable from this TB coming from SU2.
But your one of the main goal is also want to measure the primordial tensor mode,
yes.
R.
Yes.
And then that actually introduces this bifringence. So main contribution comes from the phi inflaton. In addition to do that, you have bifringence effect.
Yes.
So how do you separate those signals to say what is the real R, the tensor mode?
So the shape of the power spectrum is very different for bifringence part and then this part. So I don't have the bifringence part for this, but the bifringence part will look something like this.
Okay.
So that's how you distinguish.
That is in the large L.
Yeah, that's fine. Yes.
So it's also confused by the lensing. So
It's okay, we can remove lensing. No.
Okay.
Ask Christian, he will remove lensing for you.
Okay. Okay.
Okay, so we are behind the time, so let's thank the speaker again. So the second speaker is Hyun Min Lee, and the title is Light Inflaton Completing Higgs Inflation.
Okay. 어떻게? Okay, thank you very much. I'm happy to give my talk in Cosmo 2018, and this the title is the light inflaton completing Higgs inflation. So I'm not in a position to review all the nice inflation models. I could have taken effective field theory approach also, as previous speakers talked about. But here I want to be more specific, to be minimal by using the Higgs boson as the inflaton field. And I just collect my contribution to this for the last few years. The particle physics and cosmology are very correlated from the early universe in Big Bang and also down to large scale structures. And then we know that in many of aspects of early cosmology, we need new physics to have inflation also generate fermion masses. We want to understand how the Higgs boson to be much lighter than Planck scale, which is the natural scale and the standard model. And then also we need the dark matter to form large scale structures. The Higgs boson has been discovered at the LHC, and the 125 Higgs boson is very close to a fundamental scalar particle and consistent with Higgs couplings measured as predicted in the standard model. So this is the collection of the Higgs mass measurement from Atlas, and also there's some combination between the two collaborations, which pointing to the 125 GeV Higgs mass with very small errors. And also measured Higgs couplings are very consistent with the standard model predictions, as the particle coupled to Higgs boson has a larger mass. The coupling becomes larger, as you see from this plot. And the Higgs boson couplings are consistent with the standard model predictions up until now, but the precision is very important in high luminous LHC and future colliders. As the question is, the Higgs boson is the last piece of the puzzles, or there are something else? And I just look at my keyword is the Higgs boson is the key to open the door to new physics, and I Googled and I found this one cartoon. It was back in 2012. And then the Higgs has a key to open the door and to figure out new symmetries and interactions beyond the standard model. So knocking on the Higgs's door to figure out what is beyond the standard model. So one of the notorious problems in the standard model is hierarchy problem. And recently, after the measurement Higgs mass, the vacuum instability problem has been revisited. And then with higher order calculations for running couplings, we are wondering if there's a really new physics
at some high scale. Also, we don't have a good understanding how to generate the Higgs mass square, Higgs mass parameter square to be negative for triggering electroweak symmetry breaking, and the flavor purges, baryogenesis, dark matter, and also finally inflation. So as the Higgs boson is very close to the fundamental scala, what about Higgs boson to be an inflaton candidate? So cosmic inflation, maybe I don't need more exploration on cosmic inflation and motivation, but I want to say that at the time of the recombination, when the CMB photons are free to propagate through the space, the horizon scale at that time is too small to explain the homogeneity isotropy of cosmic microwave background. So there must be early period in which these all different patches in the sky must be in causal contact. So that's where the inflation story comes in. So we need to have exponentially increase in the radius of our universe due to the vacuum domination, and the number of foldings to require to be about 60. And then slow roll inflation, actually the vacuum domination is based on slow roll inflation, and the inflation must end in the end. And then the measured spectral index and the tensor to scalar ratio points to slow roll inflation. And this is a recent Planck data show that the inflation models, various inflation models can be constrained by tensor to scalar ratio, mostly tensor to scalar ratio and the spectral index. Although I haven't shown the bound on the non-Gaussianity, but you see the previous speaker have shown the bound on the non-Gaussianity. So inflation is a vanilla single field canonical inflation with a small non-Gaussianity. So there's the message from current Planck data. And of course, it's difficult to approach the inflation models from a first principle because we don't have an understanding about high-scale physics beyond the Hubble scale during inflation. So we need to take the approach of effective field theory based on symmetries and the low energy, and keeping truncate 3Ds of expansion in the Lagrangian in a controllable way. The curvature expansion and the field expansion, derivative expansion must be valid in this effective field theory. Then the question is how to control UV physics or entirety for entire range of inflaton fields. So there are many questions you can address, and there are many models for inflaton, so I don't want to address. But just in my talk, I want to consider the possibility of Higgs inflation and its consistency and UV completion. So just the minimally coupled Higgs boson, we know that Higgs boson has non-zero potential. So if you take the quartic term, in order to get slow roll inflation with the correct tensor anisotropy, CMB normalization, we need to have the quartic coupling to be 10 to the minus 12 during inflation. Or if you take the quadratic term, then the Higgs mass to be huge, must be huge, 10 to 13 GeV. But we know that phenomenologically, Higgs mass parameters and the quartic coupling have been determined already, which are hugely different from what we need for inflation. So you could think of inflection point at larger scales where running quartic coupling becomes small because of cancellation between three-level quartic and the loop contributions. So at some scale, you could be almost near scale invariant, so that the two-loop contribution, sorry, this is log square. The two-loop contribution might be dominant around that scale, But in this case, the number of folding is too small. It's just the standard model Higgs is not the inflaton candidate. So that's why, maybe for a long time, even though people introduced non-minimal coupling in early 80s or 90s, people haven't thought about Higgs as the inflaton. So, but the day Shabchnikov had it, non-minimal coupling for Higgs boson, and then just a single coupling seems to be very successful. So Higgs boson can drive in cosmic inflation because of this single coupling to gravity. And since the Planck mass becomes field dependent in this frame, you need to go to the Einstein frame where the effective Planck scale is constant. Then the Higgs kinetic term becomes non-canonical. So, and then also Higgs potential scales by this scale factor omega that depends on the non-minimal coupling. So here, consequence, because of scale factor, the large field limit, the Higgs potential becomes flat, being constant with the small corrections. So CMB normalization dictates the ratio of the quartic to the non-minimal coupling to be very small number. For that, you need the large non-minimal coupling for small order 1 lambda h. And then also, we have a definite prediction for spectral index and the tensor to scalar ratio. Probably tensor to scalar ratio might be proved in the future CMB experiment, as previous speaker said. So this is the cartoon of the Higgs potential in the presence of the non-minimal coupling. So as I said before, because of the conformal factor, as the Higgs field becomes larger than 1 over square root of psi, then you can drop this 1 in the denominator. Then the full potential becomes constant with a small correction in terms of the canonical field. So without non-minimal coupling, the Higgs potential becomes very stiff as you go to the large field. But if you turn on non-minimal coupling, the Higgs potential becomes flat as you go to the large fields. But this is not the end of story. It's just it may find for phenomenological reason. So Higgs inflation is well consistent with observation, but there's the classical level story. So we need to quantify the quantum corrections, whether the classical story is still okay. So the usual approach to pin down the quantum correction is based on power counting in effective field theory. So just you can write down the effective actions in scalar tensor gravity and truncate the stages of expansion. And assuming the truncated effective action, you can identify the interactions between this scalar field perturbation and the metric perturbation. And then then you can compute the quantum correction. So the quantum corrected effective action must be given by this as an expansion of the Planck constant. So then in order for the classical, semi-classical approximation to be valid, we need this quantum correction to be much smaller than the classical action. So that the effective interactions that we inferred from the field expansion must be constrained. This is the strategy based on actually power expansion in the effective field theory. So we can say much about non-perturbative effect in this approach, but we can still address the perturbative expansion and then infer the new physics scales. So the trouble with the large non-minimal coupling, the large non-minimal coupling to be around 10 to the 4th to explain the CMB temperature anisotropy. So here, you can identify, so in the presence of non-minimal coupling, just we are taking the Higgs field in covariant gauge and expand it together with the metric perturbation. Then you can see that there is a dimension 5 interactions between Higgs field and graviton, the trace part of the graviton. So if a graviton is on shell, then you can drop this trace part, but if it's off shell, you need to keep this interaction and then include that for scattering process. So actually this is the case in the Jordan frame. If you go to the Einstein frame, the connected term becomes non-canonical. So the non-canonical connected term becomes problematic. So in the Jordan frame, you can take the scattering process between goldstones inside Higgs doublet, then exchanged by graviton, the trace part of the graviton in the S channel. Then you can immediately see that this process, it grows in energy. If energy beyond the certain scale, the unitarity would be violated. So there's the maximum scale that in this theory within the validity of perturbative expansion. So that's why actually we pointed this problem out, and then I was thinking how to then unitarize this Higgs inflation. So in the standard model without Higgs field, we know that WW scattering, or would be Goldstone mode scattering, would violate unitarity. After including Higgs mode, we can, with the correct interaction to gauge bosons, it is possible to unitarize. And then there is no UV growth in the scattering amplitude. So in a similar way, I'm thinking of unitarizing the unitarity solve the unitarity problem by introducing additional scalar field sigma. This is based on induced gravity, but initially I took the different approach by going to the Einstein frame, because the connected term becomes nonlinear sigma model type. So it is possible to unitarize it by if you think this the non-canonical connected term is a low energy phenomena of the large global symmetry. So similar way, actually, this potential for sigma field dictates the global symmetry, then must be satisfied for in this extension. So sigma and phi determine the field space, and then the isometry satisfy this field space SO 1,5 over SO 5, which is equivalent to ADS5 isometry. Euclidean ADS5 isometry. And then, so after, if you can take lambda to be a Lagrange multiplier, simply. So after using the equation motion for lambda, you can recover Higgs inflation as an effective field theory. But as the sigma couples to gravity, sigma gets a connected term, it becomes dynamical. So then in this case, this potential is not a Lagrange multiplier. It becomes really a dynamical potential. So then if you take the full theory, Higgs moves along the vacuum manifold. So moves in the hyperbolic space. So that's why you can go beyond the unitarity scale. Actually, Higgs field here, you can start from 0, but you can go beyond the unitarity scale without any problem. So if you follow, if sigma becomes non-zero along this trajectory. But in this case, if you carefully study the inflation in this model, the physical sigma mass is tied up to inflation scale, which is 10 to the 13 GeV. But roughly, if you think of unitarization of the scattering amplitude, the new particle mass only has to be below the unitarity scale. But here, this unitarity new particle mass is just at the onset of the unitarity violation. So it is kind of constrained UV completion. And then I can compare the well-known Starobinsky R-square inflation in the perspective of UV completion. So it is well known that Starobinsky R-square inflation is due to scalar tensor theory by Hubbard-Stratonovich transformation. So you may not familiar with this name, but you can find this in the condensed matter physics. So, so this R-square term is the higher curvature term, but you can dualize to a scalar tensor theory in the Einstein gravity at the expense of non-minimal coupling to gravity and certain potential. But here there is no potential, there is no kinetic term for sigma, but they are equivalent at the level of passive integral. So the Starobinsky can be as a UV completion. That's my question. And then this guy, young Japanese scientist, Emma, and also recently this problem has been revisited. So you can write down R-square gravity in scalar dual theory in terms of sigma field, and in addition to the non-minimal coupling for Higgs field. So then these people claim that there is no unitarity problem, even in the presence of large non-minimal coupling for Higgs. So now I am puzzled about this because we thought that the large non-minimal coupling for Higgs causes unitarity problem. So then I figured out that if you redefine this sigma by observing this Higgs non-minimal coupling, then the resulting Lagrangian becomes induced gravity, as I introduced before. Then, as a consequence, non-minimal coupling is moved into the potential. So it does not appear in the kinetic term anymore. So that solved the problem. So, and then this is the nice kind of self-unitarization within gravity without new degree of freedom. But it seems that this feature is specific to R-square gravity. If you include higher curvature interactions, R cubed, etc., this feature will be gone. And then recently, I generalized this UV completion by adding linear term in the linear non-minimal coupling for sigma, because actually then the sigma, I don't introduce mass parameter in the potential. So the sigma can be very light, and sigma could get mass being proportional to the electroweak-symmetric breaking, but the sigma field can be very light. Nonetheless, it is possible to unitorize Higgs inflation. So the basic idea is that this linear coupling to gravity makes large kinetic mixing, and if you diagonalize kinetic terms, then you will have a large kinetic term for sigma field. So as a consequence, if you meet, so because of the large kinetic term, you can suppress all the interactions for the sigma field, unitarizing the theory, even if the sigma mass is arbitrarily small. So this is actually there are two parameters here, linear and linear coupling and quadratic coupling. So there is the two conditions to be satisfied for stable gravity in order for this effective Planck mass to be positive during the evolution, during the cosmological evolution. So there is an upper bound on this linear coupling, and also unitarity favors this relation between quadratic and linear non-minimal couplings. This plot shows that this favored region in which this A parameter ratio of these couplings to be order 1. Then we are fine with the unitarity up to Planck scale. And then, complete UV theory, it is possible to write down Higgs effective field theory after integrating out sigma field. Then the resulting effective action becomes something like this. Then, depending on the limit of this Higgs field, if Higgs field is very small, then we are recovering Higgs inflation with a shifted quartic coupling. So shifted coupling is proportional to the coupling between sigma and phi. So this is the three-level threshold effect due to the sigma field that shift the quartic coupling. Then the running lambda phi, running quartic coupling can be larger than what we expect from the Higgs mass measurement. So it can be larger than 0.13, then we can stabilize Higgs vacuum. And then if Higgs field value is very large, then we need to take sigma and Higgs field at the same time. So nonetheless, if you take the field space along which sigma is proportional to phi to satisfy this minimization of potential, the resulting non-minimal coupling becomes something like this, and then you have a non-analytic linear term for Higgs field in this way. So we can decouple sigma field in this regime. So then we need to include the sigma field explicitly. So I studied for most general sigma and phi field Lagrangian and potential. And then I took the scale free limit in which all the mass parameters irrelevant except this term in the non-minimal coupling. So psi1 is relevant for inflation. So I studied the vacuum structure for two-field space by ignoring the non-minimal coupling for Higgs, and there is no unitarity problem. And then in general, inflaton is the Higgs sigma mixed or sigma field only. And I can describe the effective Lagrangian for single field inflation with the extra terms, corrections proportional to the linear non-minimal couplings. If I set linear coupling to 0, then I will recover the Higgs inflation. So this is my final slide. So here, so this A parameters tells us the size of the linear non-minimal coupling. So if this A parameter close to 1, then unitarity scale is closer to the Planck scale. If A is smaller, becomes smaller, unitarity scale becomes very small. So here also I plot the predictions for tensor to scalar ratio and the spectral index as a function of the unitarity scale. So if you increase unitarity scale, then the tensor to scalar ratio can be as large as 0.01. The Higgs inflation predicts tensor to scalar ratio to be 10 to minus 3, but here becomes larger, then it could be better detected in the future same experiment. So let me conclude now. Higgs inflation needs UV completion. To solve the unitarity problem, I introduced a general form of sigma models. So sigma Higgs field coupling to Higgs required for unitarization naturally solve the vacuum instability problem. And the newly introduced linear couplings widens the parameter space for UV completion, including the possibility of light inflaton. So light inflaton could play a role for electroweak phase transition due to the Higgs coupling, and then it can be produced or it can affect Higgs production. Okay, thank you very much.
It's time for question. Okay, please.
on the perturbative unitarity, I think there is an argument that the kinetic time of the scalar field is modified due to the background field, and then some people argue that there might not be unitarity problem. But do you have any comments on such an argument?
Yeah, of course, I know that argument.
This argument, yeah.
Yes. So kinetic term depends on the Higgs field values.
Yeah, and the first time also gives the kinetic term.
So yeah, unitarity scale during inflation can be larger than what we identified here.
Yep.
But still, it is smaller than the Higgs field values during inflation. But of course, there's crossing. So during reheating process, you have to. This problem, unitarity problem, is more serious because you need to take into account this higher dimension operator.
Yeah. So the previous slide you showed that the possibility there are higher order corrections, and I agree that if there are such a coupling, there are higher order or higher terms, then the unitarity problem would appear.
Yeah.
Okay, thanks.
Okay. Yeah.
Yeah, maybe a related comment from the term that you have boxed in the middle of that slide.
Yeah.
I can see that you have actually implicitly assumed that the connection of the theory depends solely on the metric, on the space-time metric. But actually, if you relax that assumption and allowed the connection to be a function of the Higgs field as well, you would get somewhat different results. So my comment, or my purpose is just to make a comment that there is no just one Higgs inflation. So that if you allowed this modification, you would get entirely different results. So I think that it would be interesting to consider that as well.
Okay, thank you.
Other question? Please.
Yeah, very nice talk. So, yeah, one question, more clarification. So you complete with this light field, with this sigma field, and then it's this sigma field that plays the role of the inflaton at the end, right? So, sort of related. So you still call it Higgs inflation, but then I guess both free heating and inflation is driven by this sigma field at the end.
Yeah, sigma. I think the sigma couples to Higgs field mostly. So, but the Higgs has. I didn't put here Higgs potential, but the Higgs has its own potential, which is comparable to the one for sigma. So they have a comparable initial potential energy. So they could reheat at the same time. In the sense, the sigma and phi mixed. This Higgs field coupled to the standard model particles. The sigma couples to phi field.
Yeah, exactly. No, just because, I mean, usually the advantage and the fact to be minimal with Higgs inflation is the fact that you know all the couplings with the other standard model particles, so you know how to, in principle, do the reheating and etc. Right? Once you introduce a sigma field, there is a new sector that is completely unknown to do reheating.
Yeah, it is. It may be unknown to do unknown, and then there's a free parameter here. I didn't put here, but later on, I put A here. So this A parameter is unknown unless we know the precise number of the Higgs quartic coupling. So yeah, I agree that there's some. But so if this sigma field is light, then there's a way of measuring this coupling. So because the sigma is light, so maybe then it is possible. Okay, thank you.
Okay, the time is up. So let's thank the speaker again. And we closed the session. And now we have some announcement from the organizer.
Okay. Hello. I first have to tell you that there's some flood in the main building because of the last night's heavy rain. So be careful of your step. It's very slippery. But cafeteria, fortunately, is working. But if you want the special dietary food in cafeteria, please ask in the registration desk. And you don't forget that 1 p.m. at the front of the cafeteria, there will be a person from CUP, COP, will waiting for you for the COP tour. If you like to go to the COP, the underground physics lab tour, you can follow him at 1 p.m. after the UA lunch. And another thing is that we have a CAPP Action Lab tour in Friday, which is actually part of excursion to the Gongju. And if you want to participate the Gongju excursion with the lab tour, please sign up a desk. But if you want only visitor cab, that means action tour and don't want to go to the excursion, please tell her before you go for the lunch, because they want to know how many people will come from the action lab in Friday. Okay. Thank you.